Okay, welcome to the second half of Chapter 10. We're going to talk about Lewis structures, how to make Lewis structures. And Lewis theory is fundamentally wrong. Okay, so it's fundamentally a wrong theory, but we still use it because it's very useful. Uh, Molecular orbital theory is that combined with quantum mechanics, that is the best way to describe atoms and molecules. But why are we teaching it to you if we know it's wrong? It's because it's very useful and it works the vast majority of the time. But okay, so here are the rules for writing Lewis structures. First one is to get the skeleton, to write the skeleton out. And the hint right now is, typically speaking, the larger and or least electronegative atom is the one that's in the center. And then sum up the valence electrons, place octets on the outside of the molecule, and then add double and triple bonds as needed to get octets. Last step is to minimize the formal charge and to put the formal charge, the most negative formal charge, on the most electronegative atom. And there's a general trend with this. Hydrogen and the halogens tend to bond with 1. Oxygen family tend to bond with 2. Nitrogen family tends to bond with 3. And carbon tends to bond with 4. And there's a problem with Lewis theory, and they already knew it going in, that there's this resonance structure. So with ozone, here's the structure for the Lewis structure for ozone. So which one is okay? Should I put the double bond on this side, or should I put it on the other side? And I have to put. So the way they solve this problem, say, you know what? It's a blending of the two, and that's known as a resonance structure. So just like you have here, 2 dogs here making a third dog, is kind of like a blending between the parents. Likewise, we have the blending of the molecule there. Okay, writing resonance structures, write the Lewis structure for nitrates. So we're going to write the Lewis structure for nitrate, include resonance structures. So we're going to start with the skeleton. So nitrogen, oxygen, oxygen, oxygen. The big atom is in the center. Nitrogen is bigger than oxygen. Now we're going to sum up the valence electrons. Nitrogen has 5, and we have 3 times 6 for oxygen, plus 1 because of the -1 charge. And where am I getting the 5 from? I'm getting the 5 from, where's my periodic table? Right here. Oh. So nitrogen, 1, 2, 3, 4, 5 for nitrogen, 6 for oxygen. Notice also 5A and 6A. So that is where we get those numbers from. So this is 24 electrons. So we have 24 electrons to place, and each line is 2, so we've already placed 6. So let's place the other 18. So 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So you've placed them on the outside, giving the outside atoms octets. Now we have to look to see, okay, let's take a look. Oxygen all have octets, they're happy. Nitrogen has only 6, so it's not happy. So we have to add a double bond. So this is a fun thing about this. I can paste this. Fun thing with an iPad. Okay. So what we can do is we can put a double bond. But why put a double bond there when you can put a double bond here? And why can't we put it here? And the answer is we can, and then typically you put brackets around it and put the charge like so. And then we use this double-sided arrow to indicate a resonance structure. like so. So that's how you do this one. And it's the same as the book said. Okay, so let's see how you're following. What is the proper Lewis structure for hydrogen cyanide, HCN? And the hint with this one, at this point in time, just count the number of electrons. And if you count the number of electrons, this is the only one that has 10. So the other ones are proper, well, except for B. That's definitely not proper, but the other ones would be proper if you had extra electrons. Okay, so moving on, talk about formal charge. So we've talked about counting electrons before. We've talked about oxidation numbers. So oxidation number, and with the oxidation number, it's one atom gives its electron density to the other atom. So, but this time though, we're talking about formal charge, and the way formal charge works is that the atom gets 1/2 of each bonding electron plus all of its lone pairs, and then you compare it to what it originally has. So like here for nitrogen triple bonded, nitrogen will get 2 of the lone pairs and 3 of it originally has. Nitrogen originally has 5. It has 5 in the bonding, so its formal charge is 0. So here are 3 different Lewis structures. Which one makes more sense? So I tried to show this with different pictures. Here are the 3. So option A, we have oxygen single bonded to carbon, triple bonded to nitrogen. We have oxygen and nitrogen both double bond. Then we have triple bond oxygen, single bond nitrogen. It's carbon all in the center. So let's look at how this works. So for structure A, it's oxygen, carbon, single bond. Here in the blue on the left is the oxygen. It has 3 lone pairs. That's 6 electrons plus 1 from the single bond. Oxygen normally has 6. That has a formal charge of -1. Carbon is 4 bonds. All gets 1 electron each. It starts with 4 electrons. Has a formal charge of 0. Nitrogen has a triple bond. So it's 3 electrons from that plus a lone pair. So that's 5 electrons. Starts with 5. Formal charge is 0. Option B, you have oxygen has 2 lone pairs and 2 bonds. That's 6 electrons. Starts with 6. Has 0. Carbon is the same. It has 4 for all these options. And then nitrogen in this case has a double bond. It has 2 lone pairs, so that's 4 plus 1 from each bond, so that's 6. 6 electrons. Normally has 5, so that formal charge is -1. And then here, the last one, triple bond oxygen. Oxygen has 1 lone pair and 3 electrons. Has 5 electrons. Normally has 6. That means the formal charge is +1. Carbon still the same. Nitrogen has 6 electrons in lone pairs, 1 bonding, 7 electrons. Normally has 5. Formal charge of -2. So minimize formal charge. This one is out because it's got a large formal charge. Now we're gonna look at these two. We have a formal charge of -1 in the oxygen or a formal charge of -1 in the nitrogen. Which one do we pick? Oxygen is more electronegative. So because of that, this is the right one. It will go in this one here because option A is the best because it puts the more negative formal charge on the oxygen atom, and the oxygen atom is more electronegative. Okay? So let's see if you follow. What is the formal charge of the central atom in ozone? What's the formal charge? And the answer is +1. It has 1 electron from each of the bonding, plus the 2 there, so that's 5 electrons. 5 electrons starts with 0 or 6. It's +1. Okay. So let's go on. Let's talk about some exceptions to the octet rule. The first one we're talking about are odd electrons, and these are also known as free radicals. So let's draw some Lewis structures. So nitrogen monoxide, nitrogen has 5 electrons, oxygen has 6, so we have 11 electrons, and it's going to be nitrogen connected to oxygen. We have 11, we have 2, 4, 6, 8, 10, 11, and oxygen has an octet, nitrogen has 5, so we're going to double bond it like so. And so nitrogen has 7, it's close to 8, but that's about as good as we can get. Nitrogen dioxide, put the big atom in the center. And we have 5 plus 6 times 2. This is 17 electrons. And so, so we have 4, 6, 8, 10, 12, 14, 16, 17. So we need a double bond, and then we're going to have a resonance structure with this situation. Okay, so that is how you do both of these. And with free radicals tend to be very energetic and very reactive, and they do occur naturally. And we see this in our body as well. So we do have some free radicals in our body, and it helps with our aging process. So it causes cellular damage. And our body protects itself from free radicals by using a certain type of vitamins called antioxidants. So antioxidants, another name for antioxidants, is a reducing agent. So antioxidants are reducing agents. And so and how they work. So vitamin C is our primary antioxidant. So let's say I remember doing outreach with grade school kids. Like, man, they're crazy and they're hungry. So imagine I have a group of hungry fifth graders, and they're coming into my classroom, and I have a big plate full of Brussels sprouts. And you're hungry enough, you'll eat anything. Even kids will eat Brussels sprouts if they're hungry enough. So how do I keep these students from eating my Brussels sprouts? Well, if I put a bunch of Halloween candy in front of the Brussels sprouts, the kids will go up and they'll eat all the Halloween candy, and when they eat their fill, they're not going to touch the Brussels sprouts because they've eaten all this candy and they're not hungry anymore. So how do I protect my cell's DNA from free radicals? Well, I put vitamin C in front of them. So the free radicals will react with vitamin C, and once they react, they're gone. So the vitamin C gets destroyed, and it protects the DNA from the free radicals. So that's how it works. And there are certain fire types. They're known as halons. I'm sorry, fire extinguishers. They're known as halons. What do halons do? Halons release halides. Halides like fluorine, chlorine, bromine, iodine. So what they do is they stop the chain reaction. Maybe you've heard of the fire triangle. The fire triangle is heat, oxygen, and fuel. And the idea with the fire triangle is if you remove any part of the fire triangle, you will put out a fire. So when you throw water on a campfire, what do you hear? Steam. It turns the water into steam. That steam is taking the heat away from the fire. Will put the fire out. You can put out a fire by smothering it. So if I have a candle, I can put a jar over the candle. Say I have like a tea light candle, and I want to put out the tea light. What do? I put a mason jar over the tea light, and then it'll burn all the oxygen. The fire will go out. And fuel, say I don't want to, say I have a campfire and I want the fire to go out. What do? I don't put wood on the fire, and the fire will burn itself until it runs out of fuel. Once the fuel is gone, the fire goes out. So the last step is chain reaction. If you can stop the chain reaction, the fire will go out very quickly. And that's what halons do. When they heat up, they release halogens, and then the halogens attack the free radicals that are part of a chain reaction, and the fire goes out quickly. And I remember that's a scene. The halons are released, and in Terminator 2, I love that movie. Terminator 2, when they're in the Cyberdyne systems, and they blow something up, and then the halons are released, and the Terminator, of course, is not bothered by the halons. But the humans, the puny humans, need to have gas masks. Great movie. Anyways, we also use these. So where else do we use free radicals? We use that in SF6. I'll talk about it when we draw the structure for SF6. It's part of our stealth technology. Okay, so other things we have incomplete octets. So the boron and aluminum do this, and the way this works, so we have boron trifluoride, same thing with aluminum trichloride, and boron has 3 electrons plus 3 times 7, but actually the same thing for aluminum. And so 21 plus 3 is 24 electrons. And so each of these, so the boron trifluoride, we place 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So it plays 24 electrons. So are we going to go ahead and put a double bond here and then have a resonance form? And the answer is no, we are not. So boron trifluoride just exists here as a 3. It's an incomplete octet. Same thing with the aluminum trichloride. And the next thing, you're like, wait a second, this is a metal and a non-metal. What are they doing bonding covalently? Well, you know what? I think I mentioned this before. They can. They can and they do. Generally speaking, they can do more of a transfer of electrons, but under certain circumstances, metals, non-metals can covalently bond with each other. So metals can covalently bond with metals and non-metals, but generally speaking, they do not. But these are incomplete octets. Aluminum trichloride, this is interesting stuff. It will clot blood very quickly. So you can put, if you're bleeding, they can put that on you and your blood will clot very quickly. Expanded octets. So this only works if the central atom is in period 3 and beyond. And the reason for that is because the d orbitals, the empty d orbitals, can then interact. But this only works for periods 3 and beyond. And phosphorus pentachloride. So here you have phosphorus in the center. And you have 5 electrons from the phosphorus plus 5 times 7. So 5 times 7, 35 plus 5, this is 40 electrons. So we've already placed 5 lines, that's 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. Okay, so each of those are placed. And next chapter, we'll talk about the structure. This is actually known as a bipyramidal structure. And sulfur hexafluoride, so we have sulfur with 6 fluorines around it. And we have 6 plus 6 times 7, so that's 42 plus 6, this is 48 electrons. And we've already placed 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48. All of them are placed, and then we have the expanded octet. SF6 is part of our stealth technology as well. So it's an interesting substance. Actually, I got a video of this. Let's see if I can. Where is my educational? We have SF6. Is it sulfur or is it fluorine? Sulfur. Oh, here we go. Here is SF6. You can. This is Theodore Gray. Let me give you a credit here. Credit where credit is due. So this is SF6 is in there, and he's putting aluminum foil in here, and you can pour it, and it causes it to sink. But we use this as part of our stealth technology. Our stealth technology is a couple parts. The first part is the stealth fighters and or bombers. They have a material in it that just absorb microwaves. So they absorb microwaves and they're layered. The other thing is the way that the angles on the aircraft are, if the microwaves do not get reflected back to the source, they get reflected somewhere else. And the last thing is in the fuel, we have very clean burning fuel because so maybe you've heard of something called a heat seeking missile. What they're looking for is the soot. That it's not really tracking heat; it tracks the soot coming from a jet engine, and that's how most radar stations actually work, is they look for that. And what sulfur hexafluoride does is it releases uh, a fluorine radical, and then that causes the fuel to burn very cleanly. It doesn't. It stops the combustion outside the chamber, and it really shuts down that combustion. It shuts down the production of soot. And we see sulfur hexafluoride sometimes in the atmosphere, and that's our fault. That's the United States' fault because we're flying our stealth planes there, basically. So the world knows that. They're like, gee, United States, where is this sulfur hexafluoride coming from the atmosphere? Like, no, 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 no. It's our stealth fighters. Okay, so let's do this. Let's look at something else. Let's write a Lewis structure for xenon difluoride. So the way we do this, so big atom in the center, and xenon has 8 electrons in 2 times 7, so 14 plus 8 is 22 electrons, 22 electrons here. So we placed 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. So that's how we would draw that. Put the expanded octet. Has to be in the period 3 and beyond. And again, how am I counting the electrons for fluorine? 1, 2, 3, 4, 5, 6, 7. For xenon, 1, 2, 3, 4, 5, 6, 7, 8. I'm counting across the periodic table using the S and P block. So, okay. And our last topic, we're going to talk about our average, actually, no, second last. We're going to talk about bond lengths too, but average bond energy. So if you take a molecule like methanol, I'm sorry, this is ethanol. I need to know my alcohols. What am I thinking? Here is ethanol. And if you look at this, so if you look at the carbon-hydrogen bonds, although these two bonds are different, because in this molecule, actually, the electron density is going to kind of flow towards the oxygen, because oxygen is a very electronegative atom. But if you look at the energies, and the energy is the amount of energy it takes to break a bond. So average bond energy, kind of like if you want to if you want to break up a friendship, it's kind of like, okay, tell you what, if I give you $20, will you never hang out with this guy again? You're like, all right, sure, I don't like him. Give me $20. Like, I really like this person. Make it 10,000, and I'll do it. That's a stronger bond there. It takes more money. So same thing with energy. So the higher the energy, the harder it is to rip two atoms apart. So the average of all these carbon-hydrogen bonds have been taken and given this value here, and this is an estimate. So this would be like that number there, and it's an estimate for the bond strength. And then the heat of reaction is going to be the number of bonds broken minus the number of bonds formed. Because this is a positive, it takes energy to break bonds, and then that energy is released when it's formed. So let's do this for steam reformation. And this is, in fact, how we get hydrogen. So the book is doing something right. Use the average bond energies to calculate the heat of reaction for this molecule. So we have to go through and, well, I've gone ahead and written the Lewis structures because you need to know the Lewis structure for that. And then you have to count the number of bonds. So the number of bonds broken, so there are, we can use colors. There are 4 carbon-hydrogen bonds, 4 oxygen hydrogen bonds, single bonds. there are 4 hydrogen-hydrogen single bonds. And what color? I'll do lime green. And there are 2 oxygen-carbon double bonds formed. So bonds broken, there's 4 CH bonds plus 4 HO bonds minus the quantity 4 H bonds plus 2 C double bond O bonds. Like that. And I'll do the color coding so you can see where I'm getting these. Then you put in the numbers from up here. Let me see if I can see this a little bit better. And okay, so the carbon hydrogen bond is going to be 4 times 414 plus 4 times carbon oxygen. Hydrogen oxygen. I'm looking at my book. 464 minus the quantity 4 times hydrogen 436 plus 2 times the quantity 799, and that is exactly, I'm using the exact value for CO2, not necessarily the average. So it's partially the average, and if you throw that in your handy dandy calculator, you will get your delta H to be 170 kilojoules per mole reaction. Okay, so recap with this one. You have to draw the Lewis structures. So you're given a reaction, draw out the Lewis structures, see what bonds are broken, which ones are formed. It's the bonds broken minus the bonds formed, and then you put in the average bond values and you get the answer. Let's see if you can figure out how to do this one. The heat of formation of ammonia from hydrogen and nitrogen based off the average bond energies. So you have these here, and once you give it a try, pause it and give it a try. If not, I'm going to talk. You're breaking bonds. You're having a nitrogen triple bond. You're breaking 3 hydrogen bonds, and you're forming 6, 3 in each ammonia, nitrogen-hydrogen bonds. So then you put the 946 plus 3 times 436 minus 6 times 389, and you get negative 80. So, okay. All right, moving on, average bond lengths. So I've said this before, but atoms and molecules are a lot like people. So, and the more bonded you are to someone, right? So we describe it as closer. So you say, you're like, hey, this is my friend, or this is my close friend, or this is my best friend. You know, kind of like, let's say you casually see someone. You know, I haven't seen the person in a while. I'm like, oh hey, you're a colleague. I like you. I haven't seen you all summer. I'm gonna wave at you. You know, maybe if you're a really good friend, I might go up and, like, if I really like you at work, I'm gonna go up and shake your hand. If I see like a old school buddy that I used to hang out with, like, oh man, come here, give me some love, and we hug or something like that, right? So kind of our distance that we have between the two of us is, especially when we interact, is a sign of how much we like each other. And also another, flirtation technique 101, if you're close to the person, you show interest. Be careful with that rule though, because you don't want to freak someone out. But generally speaking, one of the ways to flirt with someone is to occupy his or her space. So, okay. So, but you can see here with the bond lengths. So you look at here the carbons that the more strongly bound they are, the closer they are to each other. And generally speaking, the closer you are, the stronger the bond. But that is not entirely true. So this is true for the carbons. But if you look here for nitrogen halides, this is not a smooth trend at all. So it doesn't hold true for all bonds. It's a general trend, but it's a general trend there. So, but I think it's a funny story, anyways. Okay, so one more chapter this semester. We're gonna go on to chapter 10, or I'm sorry, chapter 11. We're done with chapter 10. So sounds like we're going to chapter 11. Sounds like we're going bankrupt. Chemistry is not bankrupt, folks. Don't worry. So one more chapter to go, and I will see you for our next chapter.